Okay, we live? Yes, good morning, everybody. Thank you for joining us. This is a double poster roundtable this morning, which will cover two themes. The first one is theme 2.1, characterization of treaty-relevant events. The second one is theme 2.5, lessons learned from historic nuclear tests. Here from Vienna, it is me, Mario Zampoli, and Martin Kalinowski. We will do it like this. Topic 2.1 will be chaired by me, and topic 2.5 will be chaired by Martin. Without further ado, let us start with the first presenter, who is Stephanie Donner. Please, Stephanie, if you wish to share your slides, the floor is yours for 2 minutes. Thank you.
Thank you. So good morning, everybody. And I'm sorry that you can't see me, but I think slides are more important than me, and I'm just sharing them. My name is Stephanie Donner from Federal Institute for Geosciences and Natural Resources, BGR Hannover, the NDC of Germany. And I'm present our work here on the improved resolution of the isotropic seismic moment tensor part using rotational ground motion measurements. So we all know that to discriminate if an event was explosive or something else is one of the key features or key tasks to verify a nuclear test. So one of the main components of the CTBT. And seismic moment tensors are actually a very great tool to do so. However, the isotropic part of the source, which is shown here on the lower left, is the one who stands for the explosive character of an event, and it is unfortunately also the part of the source which often lacks resolution. And on this poster, we want to demonstrate that rotational ground motion measurements could bring more resolution for the moment tensor in general, but also for the isotropic part, the explosive part of the source. So rotational ground motions are defined as the curl of the translational wave field of a source. So they are composed by space derivatives of translational ground motion u, and the horizontal components of rotations are the already well-known tilt components, and the vertical one is the torsion. So rotation brings additional information on a vertical displacement gradient, and this is an information which is usually not available from translational measurements. And they have a very high potential to bring more resolution on the seismic moment tensors. Here we show this with a synthetic test which is set up in the Korean peninsula. We use two events, namely the nuclear test from 2013 in the north and a strike slip earthquake from 2016 in the south. So we have inverted 3 component waveforms using only the translational data, and also 6 component waveforms, which is then translational plus rotational component waveform data. And the necessary Green's functions to do waveform inversion we have calculated based on a 1D and 3-dimensional velocity model here. So if you're interested on the results, I welcome you to come to my poster and discuss with me, and I'm happy to take your questions. Thank you very much.
Thank you so much, Stephanie. Very interesting. And it's nice to see some handwritten equations too. The next presentation is going to be Aurélie Guillem-Trilla on rapid and automated full seismic source characterization. Please, the floor is yours. Hello?
Sorry. Yeah, so sorry. I'm Aurélie Guillem-Trilla, and it looks like I cannot share my presentation right now. So it's a bad thing. Anyway, I won't lose more time. My presentation is on moment tensor inversion. It would be nice if I can share it.
If it does not work, please feel free to speak.
Okay, so it's on moment tensor inversion, focusing on North Korea region, and we are working on finding a way to rapidly detect and characterize seismic events in North Korea. And so for that, we are also doing moment tensor inversions. And we have shown in the past that moment tensor inversions have helped to identify the source of DPRK events. And so what we are trying to do is to develop and implement at CEA an interactive tool for seismic analysts, as moment tensor inversion are often done by a senior seismologist, or also called expert. Anyway, I'm working with a method called GridMT, which means grid-based real-time determination of moment tensor. And it's a successful approach for monitoring, for earthquake monitoring, for tsunami monitoring. But as I'm showing in this poster, I invite you to go see it. We also show that it's also successful at detecting and characterizing North Korean nuclear tests. From 2006 to the last one in 2017. So it's based on using only 4 regional stations, using a 1D velocity model. It's a very fast approach. Within a couple of minutes, we can get a detection of an event and a moment tensor solution for this event. And we get also the location of the event because we are working on a grid of point sources over here, North Korea in this example. We can focus on only the shallow seismicity of North Korea for the focusing on the detection of North Korean nuclear tests, but we can also work for deeper events such as the earthquake Stephanie showed in South Korea, the one that occurred in September 2016, and we can also identify it as a strike slip earthquake. So I invite you to go visit the poster and to actually check the results. And if you have any question, please ask me. Thank you.
Thank you so much. The next speaker will be Ole Ross on ATM for potential release and detections possibly connected to the DPRK tests. Ole, the floor is yours.
Good morning and thank you. We have heard already yesterday that at 2 DPRK tests, it was possible to detect the isotopic signature of a nuclear explosion, which was 2006 and 2013. But also for check the consistency of those, but especially for the other ones where we had only xenon 133, it's of special importance to disfavor or feature background sources. And so as soon as it will be available on the live platform, you will see many examples here. I just showing the last one for the 2017 test. For the forecast of a prompt release, we had no detection. But later on, there were national announcements of South Korea that they measured some xenon 133. But if we do backward modeling for those and overlap the source regions of the samples, it indicates that there is rather another source than the test site in the source region. And later on in 2017, then we had the kind of sewage or leakage of small releases, perhaps from the test site. At least we had meteorologically consistent detection at Usurisk, where then the atmospheric transport modeling shows consistency. But even more important in the other years, 2013 and 2016, where it was used to check for background sources. So we put a lot in this presentation. As soon as you can download it, you will see many of our ATM results done by HighSplit in the aftermath of the DPRK nuclear tests. Thank you.
Thank you so much, Ole. Wonderful. The next speakers will be Martin Kalinowski a few times because he's presenting different posters. So Martin, the floor is yours.
Okay, thank you very much. And I'm sharing this slide here. So this is the presentation on the project that we do with Lawrence Livermore National Laboratory. And this mode, presentation mode. And this is a conceptual work at this moment intended to do what we present here, connect the underground nuclear explosion scenarios that the Lawrence Livermore National Laboratory is developing for all the processes that can happen underground for the formation of the radioxenon isotopes and also other isotopes actually, and the transport to the surface, and then we will have a confining boundary of what kind of isotopic ratios could possibly be emitted from all kinds of nuclear test scenarios. This can be refined with post-detonation information later. And this will be connected with our work of equations from the isotopic analysis and the sample, and what is the atmosphere during sampling time, and what are the ratios during, and how do they change over transport time through atmospheric transport, so that we can have eventually hypothesis testing whether observation is possibly matching the domain of possible scenarios for nuclear tests. And alternatively, we of course have to check for other possible sources. But this project focuses on this. That's this one.
Thank you, Martin. We'll go over to the next.
The next one was for a 6 kernel density estimation. I'm doing together with Boshue Lu, also at the IDC. And you know that we have we have established an emission database from civil nuclear releases from nuclear reactors, from isotope production facilities. And it's difficult to define a standard release amount that comes from any of these typical facilities. So what is a typical release from a nuclear power plant if you don't have the real emission data? And instead of using a single standard value, which is a fixed value for a reactor, it's better to use a distribution. And how do we get the distribution, like a probability distribution for the releases from nuclear power plants, from nuclear research reactors, from medical isotope production facilities, if we don't have observed release data from these, or reported release data from these facilities, we use the sum of all release data that we have, and then we apply the kernel density estimation method to develop a description of the distribution of the isotopic releases from these facilities, and then we can apply also the KDE to the ratios. So that's what we presented this poster.
Thank you, Martin. And now we're over to the third one.
And I can already announce there will be a fourth one, which is not in the list, but belongs to the same session. So the third one is three-dimensional space analysis. And this is one step further from the well-known four isotope plot, which is still a two-dimensional projection of a space that has more dimensions. And if we use all dimensions and do not lose information by doing a certain projection of just two axes of isotopic ratios, we can gain a bit more quality and information and output. And what we do is we project, we construct a new axis that eventually for infinite time is aligned with the decay of the respective radioisotopes in the ratios of this three-dimensional space. And then we just do a projection along this this line, and this results in a time-independent plot where we don't need to know at what time something was released, and we can still distinguish between different clusters or domains clearly what is a nuclear reactor domain, what is a nuclear explosion domain. And we can also use this axis by projecting the isotopic ratios on this axis and then do timing equations, apply timing equations on this axis to determine the event time of a nuclear test for which we have recorded releases. And we apply this to about 100 releases from Nevada. And we get a very good agreement between the origin time of the test and our estimated time from the isotopic ratios. The accuracy goes down to half an hour accuracy. That was the third one. And then I turn to the fourth one. This is a very interesting topic because it addresses the question of what is the source of xenon-135 that we often see, not so often, but that we see more often than we can understand, specifically in Japan. And now with the transportable noble gas system campaigns, we see it even more frequently, but it's also at the Takasaki IMS station. Not only is xenon-135 observed frequently, it's also sometimes seen alone without xenon-133. And the ratio of xenon-135 over xenon-133 is extraordinarily high for fission. But one needs to understand that for activation, xenon-135 and xenon-131M are the lead nuclides, not xenon-133. So for activation sources, it is expected that xenon-135 is occurring at a higher activity than xenon-133. And there is a spallation neutron source in Japan at the J-Park facility. And we test the hypothesis whether emissions from that source could explain observations of xenon-135 at the Takasaki IMS station. And the answer will be on the poster. So thank you for your attention.
Thank you, Martin. At this point, I just need to ask a question. I see Professor Dayashankar is connected. May I ask if do you have a poster in 2.1 or in 2.5? I cannot hear you.
2.5.
2.5. Okay. Wonderful. So we will have to add this at the end of 2.5. Wonderful. At this point, thank you. I pass the ball to Martin, who can chair the talk for session 2.5. Thank you so much, and we'll see each other again for the question and answer.
Thank you very much, Mario. So 2.5 is lessons learned on historic nuclear test data. And the first briefing comes from Kevin Mackey on digitization of Soviet peaceful nuclear explosion seismograms. Kevin, please.
Thank you. The Geophysical Survey of the Russian Academy of Sciences and Michigan State University are working to recover, preserve, scan, and digitize the historic seismograms of Soviet peaceful nuclear explosions, or PNEs. The Soviet Union detonated 122 PNEs from the mid-1960s through the late 1980s. The PNEs were conducted in a wide range of geologic settings and geographic locations. Thus, they represent a unique data set for geophysical studies. These explosions were well recorded by the regional seismic networks, where thousands of seismograms are still retained. In the image at left, you can see the potential data set, where yellow represents the PNE locations and red represents the recording seismic stations. We are scanning these irreplaceable legacy analog seismograms to preserve them against loss for future generations. In the image at right, you can see the scanning process being undertaken. At lower right, you can see a seismogram of the PNE Fakkel as recorded at Station Obninsk. We are also digitizing these seismograms. Our focus here is to generate very high quality seismogram digitizations that are useful for quantitative study. You can see at left part of the digitization process where we are selecting the peaks on the seismogram. These peaks are fit using a P-chip algorithm to represent a realistic waveform. One of our important aspects is that we are also recovering the original station calibration information and converting those into poles and zeros. This allows us to remove the instrument response from our digitizations. An example is shown near the center and right side of the image. I would like to point out that there are 3 other posters that complement this study, all of which are in the same poster session as this one. Thank you.
Thank you very much, Kevin. We turn to the next poster, which is presented by Josie Anderson on behalf of Luis Bernardo Martinetti. That's what I understand from preparation. Luis is also here. Quantitative research using digitized historic short period nuclear explosion seismograms. Please.
Hi, everyone. I really thank you for having me. My name is Josie Anderson, and I'll be talking about our poster. Our efforts here today are focused on seismic event discrimination between peaceful nuclear explosions, P&Es for short, and seismic earthquakes by comparing amplitude ratios of different seismic phases. We have a set of unique digitizations from the Northern Eurasia region during the Soviet era. Using these digitizations of short period seismograms, we were able to remove instrument response, express waveforms in ground displacement, rotate components, and use signal processing for analysis. We found that event discrimination using phase ratios from digitized high-frequency waveforms is a viable technique. To the left, we have a figure of meteorite 4 Mondi, where the seismogram underwent a high-quality digitization process, instrument correction, a rotation of horizontal components, and a high-frequency filter before identifying seismic phases and forming amplitude phase ratios. The top 3 seismograms are rotated. Here, they are also instrument corrected and band passed at high frequency, while the bottom 3 seismograms just show rotation here and instrument correction. Due to the high quality digitization of the short period waveform, the instrument response correction enhances the signal, as you can see by the surface waves right here. The next figure shows an example of a discrimination study with Mondi used as a data point with a high frequency of 3 to 6 Hertz. As we can see, the data point does fall within the range of explosions, thus proving our digitization technique and analysis methods are viable. Thank you so much, and I welcome any questions you have.
Wonderful, thank you very much. Next poster will be presented by Istvan Bondar, a comprehensive earthquake catalog in Central Asia. Please, Istvan. Can't hear you. Are you talking already? We can see your slide. It's not yet in full screen mode, and we can't hear you.
Can you hear me now?
Yes.
Yes.
Yes,
Sorry about that. So I'm presenting the work for providing a comprehensive earthquake catalog in Central Asia. The objective of the work is to put together a catalog for a probabilistic seismic hazard analysis, and the related poster is going to be presented by Anna Berezina about the compilation of the bulletin. The Kazakh, Kyrgyz, and Tajik NDCs in cooperation with the Michigan State University and Livermore collected all the local and regional catalogs combined with the ISC bulletin. And for the relocations, we relocate the entire bulletin with iLoc using RSTT. We select all events with magnitude 3 and above. These are the events selected for the relocation, and you can see in intermediate depths, the test distribution is pretty much flat. This contains some 250,000 events, And when we relocate the events with ILOC using the RSTT three-dimensional velocity model, then in the Hindu Kush region, which is here, the Hindu Kush Pamir region, you can see that the intermediate depth distribution changes a lot. Now we can start seeing structures. And in this figure, I'm just comparing the input data, which were the input for the relocation. When we relocate the data with ILOC using the AK135 velocity model, we get dramatic improvements. And RSTT, the three-dimensional upper mental velocity model, makes the seismicity even tighter. You can see these little clusters which are getting much tighter. So that is basically the conclusion of the talk. And if you have any questions, please come to my poster. Thank you.
Thank you very much, Istvan. The next item, the next poster would be presented from Inna Sokolova, but
yes, I'm trying to.
Was not in the
meeting. I'm trying to get rid of the. Yes, sorry.
No problem. Has Inna or co-authors of that poster large chemical explosions of the Soviet period on the territory of Kazakhstan as ground truth events joined in between since we had a pre-discussion? Obviously not. So we have a handful of more presentations coming, and I just want to remind the audience that you can pose questions through the event portal. So far, I don't see any question. We are so well going in time that there will definitely be about 15 minutes time for discussion. The next poster briefing will be presented by Kevin Mackay on behalf of Daniel Burke, and this is on applying calibrations to digitized historical analog seismograms of nuclear explosions and other important events. Please.
Good afternoon. I'm Daniel Burke, research engineer in association with Dr. Kevin Mackay of Michigan State University's Geotectonics Laboratory. Thank you for your interest in the recovery of legacy data. This presentation involves the recovery of the metadata that is important for the use of historical seismograms in the context of modern research. Digitization of analog seismograms from past nuclear tests are critical for monitoring because many historical tests occurred within unique and varying geologic environments. To utilize this historical data, it is important to know the frequency characteristics of the seismic channel that generated the seismogram to accurately recover ground motion. Calibrations can vary significantly with time and location, thus a single generic calibration for a station or instrument type is insufficient. Fortunately, many Soviet stations were calibrated annually, and these calibration records have been recovered. Focusing on stations and instrumentation from the former Soviet Union, we developed a Python-based software application to accurately translate the original station calibration parameters into modern dataless seed files. These files are then used with digitization projects in which legacy seismograms are recovered, scanned, and digitized in order to recover ground motion at the receiver site. We compare power spectral density measurements of digitized analog records against co-located digital broadband instruments to demonstrate that the process provides an accurate picture of ground motion. The resulting transformation of the digitized analog seismogram into a faithful digital rendering of ground motion can be used for advanced seismic analysis. We are now applying the correct station calibrations to several seismogram recovery and digitization projects in northern Eurasia. Thank you.
Yes, thank you very much. This was obviously a pre-recorded video of Daniel Burke shared by Kevin, if I understand this correctly. Next one is Istvan again presenting on behalf of Barbara Cheche, Seismicity of the Caucasus region, a comprehensive revised catalog for 1951 to 2019.
Hello, everybody. You can hear me now, right? Yes. So this work is done by my PhD student at the Roland University in cooperation with Theodor Godoledze Gurban-Yetermishra and Rengin-Gök of Livermore and Georgia and Armenia. And here we're presenting a comprehensive seismicity catalog for the Caucasus region. We collected different kind of catalogs. These are the Azeri catalog, the relocated Georgia catalog, and the ISC bulletin data are joined together to put together a bulletin for the Caucasus region. These are the input data for ILOC relocations with the RSTT, and on the right-hand side you can see the relocations with ILOC with RSTT. You can see even on this scale that the seismicity gets much better. The picture of the seismicity. During the relocation process, we also identified a large number of GT5 events, ground truth events, which will be important in relocation with multiple event relocations. And on the right-hand side, you can see cross sections. The first one is that the northernmost one goes through the Eastern Caucasus, and there is a clear evidence of deep seismicity there. The middle one is it goes through the Caspian Sea, so does the southernmost one. But these events we are not entirely sure because the events are already outside of the network. Anyway, the important message is this region in the Eastern Caucasus with the evidence of a subducting slab there. Using the ground truth events as fixed points, we relocated the entire seismicity of the region using BaseLock, which is a Markov chain Monte Carlo method, multiple event relocation method, which is able to relocate entire regions of seismicity. And the results show that when you are inside the network, where BaseLock makes the seismicity even further tighter. However, outside the network, the results are less reliable. And if you have any questions, please come to my poster.
Thank you very much, Istvan. I just received the good news that 400 people have joined our current e-poster roundtable, this one, and there are 2 parallel other sessions at the same time going on now. So this is fantastic. The next poster briefing is from Anna Berezina. It's a unified seismic bulletin of Central Asia using legacy data. Anna, we can't hear you. We see slides, but now they are gone.
Okay.
Now there was a sound. Yeah, we can hear faintly.
Do you see me? Do you see
Yes,
the
now we
poster?
hear you. Yeah, we see your slides. That's great.
Okay,
And we
thank
hear
you.
Fantastic. Go ahead,
Thank
please.
I would like to present the poster number 89 under the name Unified Seismic Bulletin of Central Asia on the basis of historical date. The purpose of our project is the creation of unified seismic bulletin for this territory, which will be used for probabilistic seismic hazard assessment for our region. The national data centers and seismic networks of Kazakhstan, Kyrgyzstan, and Tajikistan have digitized historical bulletins of the earthquake with magnitude 3.0 and greater for this region for 1949-2017. Data available from the International Seismological Center for all years and local digital seismic bulletins since 1993 were collected and merged with the digitized bulletins. In total, the unified bulletin contains over 10 million arrivals. To obtain regional magnitude conversion relationship for small events with traditional magnitudes ML, MB, and MS, we use the code calibration technique that allows direct calculation of moment magnitude using the code calibration tool developed by Lawrence Livermore National Laboratory. After merging all available information and relocations, the Central Asian Unified Seismic Bulletin was created. This is the first comprehensive bulletin developed for our region. This project fills in a considerable portion of a gap in the data for the region, increases the accuracy of event parameters, preserves the unique historical data, and supplements IC bulletins with new data of our region. Thank you for your attention.
Thank you very much, Anna. And the last but one poster briefing is from Kathleen Burkhardt, producing high-quality digitization from historical analog seismograms of nuclear explosions. Please.
Okay, hi everyone. My name is Caitlin Burkhardt, and I would like to introduce our poster. Numerous projects around the world have begun to locate, scan, and digitize analog seismograms, not only for preservation, but to bring this data set into the modern era. However, the successful usage of the digitized signals are based on the accurate recovery of all the possible information from the original seismograms. To date, there are no standards or procedures to accurately achieve such results. So we want to know, what are the critical variables we need to know in order to obtain truthful digitizations for our geophysical studies? One variable that we examined is DPI, or image resolution. As the DPI decreases, the pixels become larger and coarser, which result in a less defined and detailed image. This raises the uncertainty for selecting accurate points within the digitization process. So here's an example where we examine the relationship between frequency recovery and DPI, where we created a synthetic seismogram with a known frequency of 1 to 12 Hertz and digitized the signal at different DPIs. This is with an assumption of a 60 millimeter per minute recording speed. And the PSD on the right highlights the frequency recovery of each digitization. Make note that this specific example for the signal shows that a low DPI, such as 200, can recover a maximum of about 3 to 4 Hertz, whereas a 1500 higher DPI image can fully recover that 12 Hertz signal. So DPI and other variables mentioned in this poster just add to the complexity of seismogram digitization. So we invite you to come talk with us to learn more about it. Thank you.
Thank you very much. Now, before we get to the last poster briefing, for your information, we have not received any questions from the audience yet. That means we can take questions from the poster briefing experts who are in this meeting. So be ready to ask questions to your colleagues. The last presentation comes from Daya Shankar, please. Daya, it's your turn, and we can't hear you.
Yes.
Now we hear you, and your sharing is coming. Not yet. Yeah, yes, now we your slides. Good. Go ahead. Oh, it looks like a pre-recorded video that is running, but we have no sound of it. So you need to speak live, please. Yeah, we can't hear you. I see your mouse. No, that's the pre-recorded video. Yeah, the sound is not available. So please talk. Daya, just talk. Go ahead. Talk live, please. Daya, we still don't hear anything. Can you hear us, Daya? we saw your slides. So we saw your slides there. Yeah? Obviously a pre-recorded video, but there was no sound. So at least we saw the 2 slides of it, and therefore, since we cannot hear you speaking, I suggest we turn now to the discussion, and the floor is open for anyone on topic 2.1 or 2.5 who would like to raise a question to the presenters and their briefings.
I would like to make only one comment from my side about 2.5. I think it is a very fascinating topic to see how such a huge amount of data can be recovered in a reliable and precise way, and what level of effort goes into it. Also, not only recovering the calibrations and the metadata, but also really digitizing this information, which must be in various states of quality, because some of it is very old. But yes, this is definitely a very fascinating undertaking. That's just one comment from my side.
I can add on that. I think the title of the session is Lessons Learned from Historic Tests, but for me, mainly lessons learned from the effort of retrieving, digitizing, and making available data from historic tests. But also, presenters showed a lot of lessons that we really do learn, like travel time corrections. So that's fantastic to see. And since there's no other question, if one of the speakers want to say a bit more on what do you learn from these historic tests? You have already mentioned something about it, but maybe you want to highlight this again and go into more detail. Just speak up, just go ahead, unmute your microphone and talk.
Hi, this is Stephanie speaking. Maybe I have a more specific question on that topic, because so first of all, I think it's great that there is spent so much effort on digitization of this historic seismograms, and I would be interested on 2 points. The first one is, while scanning a seismograms, how do you make sure that you keep the scaling of the waveforms when you have done the digital file, a JPEG or whatever, that you know these 3 centimeters on the JPEG are 5 centimeters on the real paper seismogram? Because this is then important for removing the instrument characteristic. And the second question I would like to hear more on how do you do the wiggle by wiggle digitization of the data. So these are my 2 questions. Maybe one of the speakers can say more about that.
Thank you for the questions.
I think I can address those questions. So with respect to scaling and maintaining accurate scaling for amplitudes is very important. So in the digitization procedure that we are doing, we have an overlay template of a known size. That combined with the original DPI scan resolution allows us to maintain the amplitude scaling correctly. Basically, we're able to tie our digitization results directly to centimeters on the paper. So that is how we're doing that. But basically, there is a template overlay that we use to recover that. And you are correct that that's of critical importance, because if we don't track that, then we really can't remove the instrument correction properly. With respect to wiggle by wiggle, how we're recovering that, the digitization procedure that we are using is a manual, and we're not using automated routines. There's various reasons for that. But what we have found is that we actually choose the peak amplitudes, and we choose any inflection point where there is a change in slope. And once we have those points, we are then using a p-chip algorithm to fit a curve to the points that we've selected. We have found that that is actually a better process than trying to choose points and recover the overall curves by digitizing the curves itself. It works better and we have a more accurate representation by picking only peaks and inflection points and then allowing the p-chip algorithm to fill in the gaps.
Yeah, very good. Thank you for the answer. Stephanie, any follow-up on that, or are you happy with the answer?
Yeah, thank you for the answers. This algorithm, is this freely available somewhere?
The p-chip is a standard curve fitting algorithm. It's a piecewise cubic Fermat
okay.
interpolation feature.
Got it. Thank you.
Any other question? I have a question for Stephanie, actually.
Okay.
It's maybe out of my ignorance because I'm really an underwater acoustician and not a seismologist, not a specialist in seismic instrumentation, but to measure the rotational degrees of freedom, I imagine you need particular seismometers, or you can recover them from regular 3-component seismometers?
Both. So in fact, there are 3 methods right now. The indirect method would be to use translational recordings measured with an array. Then you can do something which is called array-derived rotation and strain, I should say. So, but this is an indirect measurement, so you just get an average rotation for the area which is spanned by your array. And then there are 2 ways to measure it directly. The first one is with huge, massive ring lasers, a technology which actually was first used by geodesy, and it was just by incident that scientists found that we can use it for seismology as well. So there are 4 or 5 1-component ring lasers worldwide so far. One in the Alps in New Zealand, one at the Bavarian Forest in Germany, Pinion Flat, California. And then we have one 3-component ring laser meanwhile, and this is standing in Fürstenfeldbruck, which is close to Munich in Germany. But as I said, these are huge, massive constructions fixed in their location. And if we want to use rotations for seismology, we need portable sensors. And these are meanwhile also available. The company IXBlue developed one especially dedicated for seismology, which is so far the only portable instrument measuring rotations in a broad frequency range with sufficient sensitivity for seismology application. There are more sensors available, but these are mainly strong motion sensors then. So yes, you need sensors, of course, but they are available meanwhile for 2 or 3 years since now.
Thank you. So yes, but it is rather that they are emerging products, so to say. They're not. They have not been around for a long time. That's interesting to hear. Thank you.
Thank you very much. Any other question from the co-authors, presenters, and each other?
If I may?
Yeah, please.
I know there's a large audience listening in, and I would encourage the audience who's viewing this session to seriously look at the potential of other legacy data that may be within their holdings. Collectively, in support of CTBTO, there's a lot of data out there from the era of nuclear testing. And I definitely would encourage different organizations to see what they may have in their archives. There could be some invaluable data there. I would also, though, like to suggest that when you have something and you wish to work on recovering it, to be very careful. I mean, the goal is to fully extract all of the usable data out of your archive in a way that can be used by the community. And sometimes it's a complex process with a lot of variables. One of the things we're trying to do at Michigan State is to understand those variables. But it's not something necessarily to be rushed into, but if done properly, there is an enormous amount of data out there in the world put away in archives that can be very important for CTBTO.
Yeah, thank you very much for this call, Kevin. Let me just add that I'm sure there's also a large amount of other data, maybe hydroacoustic, infrasound, and radionuclide, because we are focusing mainly here on seismic. But the other sensor technologies were also applied in the decades of the nuclear testing. So I'm sure there are plenty of data that those who hold them have no clue that they have a value for CTBT monitoring today. And I think we need to spread the word and need to be active, contacting experts and institutions and investigate and explore whether they could have something that they could share with the community. You want to say something on hydroacoustic or infrasound or anyone other in the group?
No, not particularly. Of course, there are data when it comes to hydroacoustic. Maybe some of those are still regarded as sensitive by the nations which hold them. But yes, all these historic data are a treasure trove. But I do have a question for Kevin. Have you recovered, you would say, a majority of the data that you wanted to recover, or how much of that was already in a state after so many years that it was not usable?
So we have several projects that are working on digitization of nuclear explosion seismograms. Currently, they're focused in former Soviet Union, in Russia, and in Central Asia, where we have several cooperative projects. We have recovered nowhere near the total amount of data that is in principle available. It is time-consuming. In total, across the areas we're working in, there are tens of thousands of nuclear explosion seismograms that could be digitized. So it's a huge data set, but it currently is quite time intensive to recover that information. So, you know, it's not at this time a fast process. Hopefully some new technologies and techniques will come online from this community that may help speed the process, but it's a significant amount of data, and much of it is still in good shape, at least for archives that have been well maintained. But to some extent, we still don't even know all of what's out there. There's still things that we find, and you know, hey, that's useful. That would be very, very good to recover. So then you add that to the list of future projects.
Thank you. Oh, sorry, we were muted. So thank you, Kevin, and thanks to all. Just a final comment, yes, on this historical data project, let's say, or these projects are also a wonderful example, I think, of open cooperation, multilateral cooperation that is really inspiring, I find. So we have been notified that our session is coming to a close. So we would like to thank all of you again for very interesting presentations, very interesting discussions, and well, we look forward to seeing you throughout the conference. Thank you so much.
Let me also suggest that if you want to continue meeting, you can join in one of the video spaces, and currently it seems 2 video spaces empty. Nobody is there. So if you walk over there and just go into this video space on the event platform, you can continue discussing and sharing information and ideas. So thank you very much for your participation.
Thank you.